Ya, Assalamualaikum warahmatullahi wabarakatuh. Selamat siang dan salam sejahtera untuk kita semuanya. Ya teman-teman sekalian, terima kasih atas kehadirannya di siang hari ini. Dan selamat datang Prof. Zulkifly. Terima kasih atas kesediaannya untuk hadir di Departemen Fisika, memberikan seminar rebuan kita. Ya, seminar ini diadakan setiap hari Rabu, memang. Jadi dan ditayangkan secara offline di sini, YouTube juga, dan online pada waktu yang sama. Sehingga materi ini bisa dilihat oleh semua orang seluruh dunia. Ya, baik, terima kasih. Nah, mohon dimaklumi kalau ruangan ini tidak penuh, tapi sesungguhnya di dunia maya banyak sekali yang menemani kita. Ya, terima kasih. Untuk itu saya persilahkan langsung saja Prof. Zulkifly untuk menyampaikan materinya. Beliau akan bicara dengan bahasa Inggris dan juga bahasa Melayu, insya Allah. Ya, jadi kalau mau bertanya nanti bisa bahasa Indonesia, bahasa Melayu juga boleh. Sedikit berbeda. Terima kasih.
Terima kasih Prof. Santoso. Okay, Assalamualaikum, salam sejahtera, and good morning, good afternoon everyone. Okay, basically I would like to thanks Pak Santoso kerana mengundang saya ke sini. Okay, saya amat menghargai datang ke sini, dan I think I really excited to be with you here in University of Indonesia, right? And then I think this first time I came here in Jakarta quite some time already, but normally I went to Universitas Tamanagara. I think I don't know, just nearby neighbors to Trisakti Universitas, right? Okay, basically, for today's talks, I'm going to touch a little bit on this particular area, what we call the advanced schooling for efficient thermal management technique. Okay, basically, my name is Muhammad Zulkifly Abdullah. I came from University Science Malaysia. University Science Malaysia in P.Eng. Okay, in P.Eng, ramai yang datang ke P.Eng untuk berobat, itu famous itu daripada Medan. Many people go to P.Eng for medical treatment, right? Okay, all right. I'm going to talk on this efficient advanced cooling for efficient thermal management technique, and this one research work that I have carried out for quite some time already. I think more than 15 years, right, in this area. I did publish a lot of paper in this one. You can also I will show to you some of my paper also later. All right. Okay. For today's talk, I will going to take about 2 hours, but my content, I will going to touch first on these particular thermal trends and challenges in electronic product, right? Why we need to study this, right? Basically. And then we're going to touch what is a thermal management for electronic devices, right? And then I'm going to touch a little bit the theory behind it, right? Theory behind it, how we're going to calculate, how to quantify whether the thermal behavior ataupun thermal management are okay or not. We're going to have some formula for that, right? And then I'm going to share to you current electronic cooling project in USM. Basically, I pick a few topics. First is about fan cooling technique, right? Fan cooling technique. Second is a PV solar cell cooling, right? Also, solar cell now become important. Many people are using the solar panel, right? But because of heat and then the performance be reduced, right? Therefore, how we going to quantify this issue, all right? Especially in terms of heat. Okay, and then lastly, well, I'm going to touch on the lithium-ion battery cooling, right? Lithium-ion battery cooling also very important. Nowadays, many people are using electric car, right? Right. Therefore, especially lithium-ion, easy to caught fire, right? I mean the fire run away. Then it is very danger how we can use the system can help or to reduce the apa to avoid this apa uh, this issue lah basically in term of to protect the battery in term of the safe condition. All right. Okay. Right. This is what I'm going to touch today. I hope will take about 2 hours. Right. From now. Right. Okay. I think if we talk about Moore's law, right? Moore's law is a founder of the Intel. Then he's predict that 220 2030 will be a trillion transistor will be put in the one chip, one package, one what we call the one device, right? Therefore, it's quite high. Nowadays, they reach about billion already, a few billion already. But in the 2030, we will reach about 1 trillion. When cost, even nowadays, also we can face a problem already with heat. If you, I think when you come across with your notebook or your computer, sometimes it hang, right? If you use a very long, especially you are doing a calculation type of program, right? Then sometimes you'll be hang, right? This is because of heat. Heat make the processor hang, right? That means you need to switch off, and then you need to on again and make them cool first, right? That's why we have many cooling device, right? They have selling in the shop. They have a fan blow from the bottom and so on, right? To cool down, right? This is how the problem we're going to face when you're going to have a more transistor in one tiny package or small package, right? Okay, this is what I'm going to talk on today, right? Okay, as we compare, if you see that a trend, this the apa, this side, it is a apa, temperature against density, right? How much transistor to put in our electronic? Normally we go to 100 watt per meter square. Our sorry, how watt centimeter square. But nowadays the power of the processor is more than 100 watt per centimeter square. Is really high. And then if we see comparable to the nuclear blast, if the heat is in the tiny, it's too hot, right? That's why we need to manage it. Without managing, and then that processor, we are not going to stand long. Right? Will be easily damaged, right? Okay. All right. That's what we're going to come. All right. These are challenges and constraints when we talk about this thermal management. We have heat flux, as you know, is in the chip and our equipment increase tremendously because everything we need fast, right? If handphone we need fast, we need a power more bigger watt, sorry, right? To make various application, not only apa in a computer, in a handphone also we can feel that hot and the heat generated, right? When you use so many quite some I mean when you're talking so long, right? This how increase in terms of heat, right? Low power semiconductor technology replaced by faster device density grow, right? And then we have heat removal technology slow to catch up. But the technology of cooling is slow, right? We need to, because people thinking what type of cooling that it's because we want to design a cooling system, we must be cheap, we must be reliable, and then sorry, right? Thank you. Right? This one. Okay. That's why cooling must be what we call it acceptable in terms of usage, and then also in terms of to make it work, right? And then sorry, okay. And then operating temperature range device have not changed much in 30 years. We try to, because normally electronic, we cannot more than 70 or 80 degrees C, the temperature level, right? Beyond that, and then we face a problem. That's why uh, there is a limitation that electronic engineer need to aware of, and then to make a proper cooling system that to maintain the temperature, right? That is the reason also. And then thermal is a main constraint and major issue, right? When we talk about this, therefore thermal is very, very important, right? We need to remove as much as possible, right? Like your car lah, right? Like engine of your car, right? We have a petrol pumping, is too hot, we have a cooling system. If cooling system don't work well, and there is burn the engine itself. Just similar to that only, right? Okay. All right, this is what failure of electronic device normally caused by temperature is the main one, right? If you see, heat is the major main contributor to the failure of electronic. Other is also like humidity, vibration, and dust also contribute, but the majority one is come from heat, right? All right, these are the relationship between heat and reliability. Therefore, we need to be must be keep temperature under control to ensure reliable operation for better reliability. You need to control the temperature, right? Okay. Even our also, right? If we stay in a hot room and then we start to worry, right? It's too hot, right? Similar to electronic also, right? We need to control the temperature. Device power dissipation are increasing rapidly with speed and device density, power growing very fast, right? And then we have also thermal issue is a major limiting factor in performance. As I say, if become hot and then performance dragging, I mean, very reduce significantly, right? That's why we need to mitigate this, right? And then thermal solution are related to physics. Of course, you are come from physics. This all physics thing. If a mechanical, it depend on the physics only, right? Okay, and then great opportunity for thermal engineer. Therefore, when we tackle this, therefore the engineer, especially in the thermal area, will be important, right? Especially in electronic industry, right? Okay, right. This is the apa heat related to. Oh, sorry. This is the what we call it. Heat will be caused by following failure mechanism. First, when it generate heat, then chemical start, right? You know, activation energy. When it heat, then the chemical will be react. Okay. We have also diffusion effect. Heat will be separate to the neighbors of the along the neighbors, right? And then we have a dielectric breakdown. Also, we have a dielectric, and then maybe dielectric also will be failed, right? And then we have ion movement, electromigration, material creep, cycling fatigue, right? Especially in solder joint, because every component they fix with solder, right? We have cool and hot, the solder also will be fatigue, right? This is the how. And then we have a board warpage, so will be bent because hot, then it's become bent, right? It deform, right? And then performance will be drift, performance will be drop, right? That's how the cost by the heat, right? And then these are in terms of equation, and then we call it reliability is 1 minus F. F is what we call it probability of failure, right? Depend on time. Depend on time is more long run. The apa? the product will become less healthy until he collapse, right? He fail, right? This is how similar to ours also lah, right? We also depend on time, right? When we grow until old, and then we also collapse, right? This is the also happen to the uh, uh, electronic. Okay, these are relationship. These are reliability. Is a E minus lambda. That is a lambda based on activation energy, right? This how exponential will be a formula like this, and then it is given by this formula, and then these are failure time, time of failure, time of at beginning, and then there is EA, and the K is thermal conductivity there, right? No, sorry, K is Boltzmann constant, sorry, Boltzmann constant, thermal, and this one is activation energy, and then because of chemical react, and then this one will be reduced in terms of time, right? Okay, this is the graph for that. Become very long, and then the product become less healthy until it fail, right? Okay, all right. Okay, these are thermal management. Thermal management is very common, right, in electronic most, because we are very lucky because in Penang they have many electronic industry around, right? And we, I think in Penang about 90% industry is electronic only, right? Therefore, a lot of issue that we share to us that we can understand how the problem the problem develop, and then we also can contribute some input to them how to solve it. All right, this is how it is. Technique is enabled to remove the heat from microelectronic device with or without the need of apply external energy to do this. Right, especially we try to develop a system. It's possible we want to be a simple one, simple and free. Is free mean that we don't need to put so many parts. Huh? That means we have a simple technique, then we can have a low cost in terms of cooling, right? These are most important. But it's not easy because certain product we have a different power, right? Different power. Anyhow, you need to have a proper one, a more expensive system that to cool, to drop that. I mean to remove the heat. Right? Okay. Therefore, we can say that thermal management can be active cooling. Right? Active cooling when you see the fan, you know, right? Every computer have a fan inside, right? You can hear that. There is an active cooling there, and then they normally they use a force convection, pump loop, or refrigerator or cooler, and very normally costly lah in terms of system, right? Compared to passive one no need only fin, right? Only fin, right? There is no external power, no conduction, no natural convection, radiation cheapest, energy free, noisy free. All right, this is how passive one. And then that if they use passive, we know that that component is not that much power. Right, it's less. Transistor is there less. They use less transistor. Of course, they use a low or passive cooling. Right, but we also can use hybrid. Right, nowadays hybrid become important. Right, it's hybrid like a heat pipe. Just now, I will pipe. They have a hybrid system. Therefore, it is very useful. All right, require input power combination of passive and active, and then also efficient, right? Therefore, when you design a product, and then you need to decide what this cooling system should be, right? But of course, you need to calculate first to ensure how much the heat generated from your device, right? That is how we start to design, start to think how what type of cooling technique that you want to use, right? All right. Heat transfer and fluid flow in electronic. This we cannot run away. When you involve with heat transfer, you must have a fluid inside, right? You must have a fluid involved. Without fluid involved, and then very difficult for you to control the heat, right? Okay. Cooling of electronic is a heat transfer field, uh, invokes all area of heat transfer such as these all. I think you learn right? In physics also I think you learn what is a natural convection. These are very simple concept of heat transfer, right? Right. And then we have a fluid flow, pressure drop, extended surface, right? Like a fin. Fin we call it extended surface, right? And then we have a center technique, empirical data analysis, numerical and computation method, and heat exchanger design. These all that are you need to know when you are developing a cooling system, right? All right. Thermal issue. Heat is empirical. You can calculate. All right. They have a right can be calculated. This can be empirical, and that there are thermal prediction with experiment is a difficult task, right? To predict a very complex system and then it is very difficult, right? This is the issue, right? Especially you have a complex geometry, bend, traction, non-uniform composite component sizes and layout, non-uniform board surface and heat dissipation, and non-uniform flow and velocity distribution within equipment. This is difficult when it become a complex system, right? Therefore, calculation are very tough. Manual calculation, right, is more difficult, right? Accurate thermal modeling is critical. Therefore, modeling is very important, right? The more simulation is very important nowadays, right? That's why in electronic they are relying also heavily on the simulation, right? Simulation means using a software, right? Good, right? And then select the right modeling tool for the application. There is no substitute for experience, right? Experience also very important. Experience engineer and conduct validation tests whenever possible. You can validate your simulation also, right? Okay. All right. Thermal issue, we have a cooling system. The cooling solution is depend on a factor such as heat flux, like I said just now, power consumption, space, weight, reliability, mobility, integration, maintenance, noise level, and cost, right? All those are, are, are important when we design. Make sure how big the size of the system, how constrain or your device put it in the contain in the enclosure or whatever, right? That is all important. Therefore, this is the main important operating costs. They are also need to look at. And then how much build cost. You cannot too expensive, because if you too expensive, your product is become out of the market. People don't want to use, right? Because become expensive, right? And then we have a product lifetime also very important. Make sure it's longer. And then we have a consumer acceptance. It must be like, must be uh, I mean, people like it. Right? Outlook must be nice also, right? This is how the engineer need to consider or to take care, right? These are thermal issue that need to be designed properly in terms of to make a proper thermal solution, right? All right, these are when, for example, these are one package, right? The package have a chip inside, right? Chip have many transistor, right? Inside the chip. Therefore, we have a normally we encapsulate, we cover with the polymer, right? And then we have a solder underneath, right? These are motherboard, for example. These are board. Therefore, the heat from the chip, these are cause heat, right? Heat start to spread either the spread through the ambient state or straight through the motherboard to the board there, right? This is how we're going to control it, right? The heat spreading, right? Which way we don't want them to go, which way we're going to quickly transfer the heat as fast as possible from the heating place. This is how we need to take care, right? This is how to ensure that keep junction temperature, this junction on the chip, device safe value, either all operating condition, to keep board below than 100 degrees C, right, if possible, right? And then important development, important deployment consideration, compliance and safety, ambient temperature, air conditioning failure, weight and mobility, altitude, solar heat, load, and cost. These all are the main factor when you design it. I mean, when you calculating the system that you want to develop. All right. Okay. For reliability and performance purposes, equipment design are ultimately interested in the device junction temperature. Junction temperature is very important. When junction temperature is high, and then people start worrying. Right. That's why I want to predict what is a junction temperature. Right. Heat is dissipated in the device junction, which is conducted through a body of the package and then leaks to the board and local ambient, right? To the board and then naturally, I mean, convection based on natural convection to the convection to the ambient, right? And then the ambient heat flow from junction to ambient through a two parallel path, either junction to the package to ambient Q1 or junction to the board through ambient Q2. This what is me. Oh, sorry. This one. This is junction temperature through Q1, right? This was Q2 through the board, right? This how we need to calculate this, right? And then the most important also is it's often difficult to separate the amount of heat flowing through these two parallel paths. To overcome the difficulty, we define the net thermal resistance. There's thermal resistance from the junction to ambient. And then the formula is these are thermal resistance, Tj temperature of junction, minus T ambient, P is power of the package. Power of the package, right? If you know that, and then we know what is a total thermal resistance of that particular package, right? This is how company measure it, right? First, they want to predict thermal junction temperature. After that, they will know how much thermal resistance for that particular device. When they know that, and then we estimate how much cooling they need, right? For that to reduce the resistance, right? Okay, this is how, because conduction you can use, and convection you have a parallel. I think you know, right? When this resistance, we assume that it is a Fourier series type of equation. Therefore, you can make a resistant type of presentation, right? Okay. This how this from apa? This from junction. This a convection, right? This how they present the junction to ambient, right? Okay, these are device. When we talk about device, they have many what we call the board level. This is a board level, right? Board, they have a board, board, and they have multi component on that, right? This is a board. Or you can say that package level, every package, right? You can study also every package, but when you study every package, we get a package level. Every package, different type are installed on the board, right? And then we have a system level. System level is more difficult, more component, right? Especially in your electronic device or whatever, computer or other instrumentation also they use the same electronic, right? Okay, I think I want to touch a little bit on this. What I'm doing in USM. Basically, this is my ongoing also, some of the project, right? Stay ongoing, right? Especially in this particular topic, effect of heat sink, heat pipe, and reflector on a PV solar cell cooling, right? This ongoing project. I have these are one of my PhD students, experimental and computer simulation of multi-piezo fan with a different configuration, right? I'm going to touch on today. And then experimental and computer simulation of synchronized piezo fan. Piezo fan also we can synchronize it to make sure which is properly or try to optimize the heat dissipation, right? And then we also have a study on heat notebook, PC cooling. I think you have a notebook, you have a cooling underneath, right? Cooling. Where normally, if high power of your computer, normally they have a heat pipe cooling there, right? And then they have a study on a fin loop heat pipe with a nano fluid on the computer. This one study on the effect of heat sink, heat pipe, and reflector on the solar power, right? Solar cell cooling. And then lastly, I'm going to touch a little bit on the lithium ion battery cooling, right? Is it okay? And the half an hour to go? No, 1 hour again. Half, okay. Okay. I thought I finished 2 o'clock, 3 o'clock, right? Okay, sorry. That's why. If not, I need to a little bit fast. All right. Okay. Now I explain a little bit what is experimental and numerical simulation of multi-piezo fan for electronic cooling application. All right. Have you heard of piezo fan before? Piezo fan is a flipping blade, just like this. Huh? Piezo, we see that. Okay. This one is not yet been utilized in the application. We just study that, right? Whether it can replace a fan cooling. Now we use a fan. Why we use a piezo fan? Because you cannot hear the noise. There's a flip only like this. You cannot hear the noise, right? Fan you can hear not the noise, right? Fan. If your computer, right, in your computer, right, and you can hear the noise. But this one you cannot hear the noise, right? Okay. This the fan actually is a ceramic material at the top. I think Pak so no this right. This has a ceramic at the top because when you normally this one when we introduce electric and then they have a bottom have a negative, top have a positive, for example, right? Therefore, the expansion of the ceramic at the bottom will be expand and the top will be contract, and then to make the like this, right? And then it's when we use a frequency and then flipping regularly, like right. This is how a piezo fan work, right? Actually, this piezo fan a lot of people used to harvest the energy. For example, energy from wind or something vibrate. For example, they put it piezo fan start vibrate. When it start vibrate, electric energy will come out, right? Electric energy. But this one we make a reverse. We apply electric, make them moving, right? This is how we utilize the piezo fan. This is a piezo fan. It's very small. We bought it. We don't do it. To fabricate this one because it's very difficult, right? Okay. There's a flipping here. There's electric you supply. There's electronic there, and then they start to flip, right? And they induce the airflow in front, right? Like we use a fan, fan, normal flip fan. Okay, this is what we try. We try both experiment and simulation. Simulation, we want to compare it and we want to explore more. Okay, experiment, we buy the piezo fan from US, right? This is the specification of the piezo fan. It's very small. If you see that, the weight also 2 gram, very light, right? And then we have a very the blade swing also. This amplitude 0.95 cm. Sorry. Okay. This is how the characteristic of the fan blade. Right. Okay. This is the setup we do it. We this a fan, and then this hot plate. Right. We use wood, and then they have a small heater at the center. Right. And then we use a controller, to control the piezo fan, right? By this digital DC power supply and oscilloscope to see the frequency, right? And then we have also a computer, because we use laser to measure the distance of piezo fan move, to make sure it's according to a specification or not, just to check, right? And then we can also can control how 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 small, how big the flipping, right? We can also make it small if you want. That's why we can control through this device, right? And then flow, we put in a container in the what we call it wind tunnel, and then we flip the flow, and then we can measure the the vibration, right? We measure the vibration also how much vibrate, uh, and then we can capture the by the what we call the uh, vibrometer, right? This one, sorry, this one is a laser. This one is laser to see the nickel mirror. This one to see the flow along induce along the plate. This one laser, they make it sheet. These are what we call it PIV, right? And then okay, and then we measure thermal performance, right? Based on this particular temperature, we have a temperature sensor, right? We have a thermocouple there on the plate, right? And then we also use a check noise level with a laser vibrometer, okay, to check whether the noise is low as we require. Okay, these are we test in this particular piezo because we want to know the specification of the or to configure configuration of the piezo, how big the flat, how many fan we want to use and so on. Therefore, we try this one without heat sink. It's a flat. This one is a heater, right? And then we try to put it fin, two fin, right? This one four fin, right? And then we put it piezo on the top, right? If we have a 3, if 4, we have 2 piezo and 4 piezo, we put it at the top to cool vertically, right? Okay, we also do some DOE, you know, right? DOE to optimization technique, right? To calculate what is the optimized in terms of distance from the tip of the piezo to the surface, and then also what is amplitude and so on, right? We can use this DOE to apa to calculate for us. This is the piezo. In the experiment, we tried three piezo. Three piezo concurrent, run concurrent, right? Therefore, we flip through, and then we measure the temperature, and then we measure the flow also, right, along that channel, right? This, and then this one also a modeling using a fluent and fluent, and then we, because these are dynamic mesh, right? When it's dynamic mesh, and then we need to have a UDF file program to have to make the mesh is moving, right? And then this is the size of computer domain, right? In the NC's Fluent. All right, this is a formula we use, right? Basically, because of we involve with heat, we involve with fluid, and then we need a continuity, momentum, and also because the energy equation is there, because the temperature is there, therefore we need to have energy equation also, and then we have solid mechanic, solid because it is solid, deformation and so on, and then we need to have a equation for solid, and then this one apa is because of the flow is turbulence, and then we give a turbulent equation there, right? Inside we supplied it inside the fluent. Okay, this result we obtain. Okay, we have a vibration on the piezo. See, this one, if you see, I can see this one is a 15 and 18 different of vibration, right? These are vibration, and then we have frequency, a different frequency give a different vibration, right? Okay, and then also if we average vibration, uh, amplitude, and then effect of field to the piezo fan amplitude. Amplitude is a linear, almost linear. If you have bigger amplitude, bigger swinging, give more vibration, right? You can optimize if you want. I think the best, this one frequency with vibration, at least at the middle, give a higher vibration, right? In this frequency. Therefore, if ever the higher vibration, we try to find the lowest vibration there, right? Okay, this is the laser PIV, we call it. We measure the flow, and then we can see the flow behavior when the apa piezo is flipping. Can measure it. This is the apa we can trace also the flow through seeding particle, and then we can see the vortex develop when the flow are flipping, right? When the piezo is flipping. Okay, and these are how we measure the temperature, because temperature is very important. We need to reduce the thermal resistance. Therefore, we see that from the beginning, we on the heater, and then the heat will be increased until certain time, and then we on the piezo. When we on the piezo, and then suddenly drop in terms of temperature. See, a big drop, big jump here, right? That means the piezo already on, right? Okay, and then uh, these are transient, this one, and then we can also measure the heat transfer coefficient, also very important, right? We can see that heat transfer coefficient are very, right, at different uh, amplitude, right? And then we see that more amplitude give more higher heat transfer coefficient, right? These are give the pressure temperature drop, sorry, temperature drop at the optimum condition. Therefore, we do DOE, and then we can find what is the optimum. These are optimum for that particular setup. All right, this is a result that we got it from experiment and also DOE. Right, we run the experiment and then we use DOE, and then this is the optimum value. We got it, right, based on that setup, right? Okay, and then we can explore effect of gap, effect of gap between piezo and the surface. And then we also study different amplitude. If the amplitude is bigger, then Reynolds number also bigger. And then we have also thermal resistance. We can also measure. And then this is the found data. That means the distance 0.03, which is the presently found to be the best, right? Between the tip and the surface, right? Okay, this one amplitude of piezo divided by uh, the gap, right? Gap is 0.3, and then we found that this is the best, right? And therefore, we can calculate, right? Those, right? And then we can also plot Nusselt number. Nusselt number also can tell us if Nusselt number bigger, that means heat transfer is bigger, right? Therefore, we can see various configuration. These are configuration A, B, and C, right? Therefore, we can see that configuration C will be highest. It's better for cooling, right? With the C mean, we for fin. One, two, 3 feet, four, 3 feet, and then 4 feet. Sorry, 4 feet, and then we have 2 feet, right? At two, and then this one C is without fin, it's lower. Okay, that's how we can also calculate comparison traditional heat transfer remover. All right, we see This is the rotary is a fan. These are piezo, right? And then we can compare. The fan is a best case, and axial fan, this one fraction, piezo fan significantly reduce power consumption compared to the axial fan, saving up to 3 to 4 times if we compare to in terms of energy, right? Power utilized, right? And then we also can play with mode, right? We have a different mode also. We have a user defined. We can play a beam, velocity, position, or different amplitude, and then we can see what is the beam velocity and different position of the beam, right? Through vibrometer, through a simulation. Sorry. This the also we can utilize using a flow visualization, how the flow looks like when come the flipping piezo, right? These are on the plate itself. These are single blade. We can see these are double blade, right? And then we can see that the heat transfer coefficient for multi has a value of 311.12 watt per meter square, while the single fan only can produce 289.57. That means by two fan, okay, multi fan, you can improve the heat transfer coefficient, right? Also, we can also effect of uh, tip gap between fan tip and flat plate. We can see also how much effect of the significant increase vorticity more than 218%, right? Is observed for the multi-fan piezo case compared to the single fan, right? Smallest gap 0.03 yield the highest convection coefficient, right? That's what we come out of the result from the experiment and also simulation, right? And then we can play a lot of things. We can also effect of piezo fan amplitude with a different Reynolds number, okay? And then we can plot configure A, configure B, and configure C, right? And then we see that configure C give higher and better in terms of performance, right? To reduce the heat, right? And then also effect of the fin configuration. We have a multi-fan, obvious configuration is outperformed. Heat transfer coefficient decrease at the move to heat sink center. And then we know that the average convection in the configuration B is 28% higher than in the configuration A, right? That is how we can come. And then we also can see also the comparison between experiment and simulation is quite acceptable, right? In terms of variation at configuration A, configuration B, and configuration C. In terms of heat transfer, also we can see quite acceptable, right? In terms of comparison, right? And then nowadays, we also can apply the piezo fan, and then we can design the fin. Whether just now we also use only one without fin, and then second fin, and then also uh, four fin. Right now we have a different type of fin we can play with. Therefore, we can have also different rotation, a different orientation to cool the heat. I mean the package, right? With a different fin configuration. Therefore, it is a very many things. I mean, more orientation that we can explore in the future study, right? Because we can redesign the fin that accommodate the piezo itself, right? That's what is good about this piezo fan, right? All right, this is a new fin. If you can use a fin something like that, and then of course we improve in terms of heat transfer coefficient, right? That's why fin design also are crucial, right, to accommodate the piezo fan, right? Okay, now I want to touch second one is about synchronize. Just now, if no, without synchronize, all right, we know that what is a synchronize? Synchronize because if you see apa feet like this, right? If you flip like this, if you are two, you can do like this, or you can do like this, right? You can do like this. This is synchronize. How you need to synchronize? Which is synchronization that give a better heat transfer coefficient, for example. Right? That is what we are studying on that. Right? Now, uh, of course, these are one of the PhD students also study on the to look at the synchronization of the film. All right. Again, these are all the issues that I already touched. These are problem statement. Of course, we want to use cooling for, right? This is the problem that we come across when we dealing with heat. We damage all those apa uh, uh, device, right? We can make a life the life of device be very short without if you don't control very well. Okay, this the can be applied in various application with TV, apa LED TV and so on, right? This is the fan we use, whether you can use a bigger blade or smaller blade, right? You can choose, right? You can buy uh, uh, the size of uh, suitable for you, right? If you compare, you see, sorry, it is very small. See, if your 20 cent small coin money just compared to peso, it's very small, right? You can you can place every small place also, right? This is my setup to make a synchronization, right? To make a synchronization, this is the peso, okay, and then they have what, and then we use a, a synchronize. These are laser vibrometer. Sorry, this one laser controller to control the laser flipping to check. This also the what we call the vibrometer to check for this one single, this one double, right? Okay, and then we see this one because we want to use PIV, and then we will reflect the laser light, and then to check the flow, right? And this the synchronized meter. We use this one to make it synchronized, right? They have a device to control the apa the piezo, right? And then this is the synchronization. Whether we go to that way, we go to this way, and then going to control, right? We can also do a different orientation. Whether it's flapping like this, we are flapping like this, and so on, right? And then, sorry, this the but we in this particular case we try to cool the LED light because the application we hope that to use in the TV screen board, right? At the back here, we have a piezo, right? Because here is all LED, right? The TV, okay? And so therefore, we try to make it LED, and then we mimic the LED. This is my LED, and then we study this one, and then we put it a different location. We study a different orientation, and then we also study a different synchronization, right? So we make up 2 and 4 condition like this, right? 2 and 4, and then we will make the piezo work now, right? And then we do some simulation also. We come up a simulation, okay? This simulation also we consider fluent NNCs, and then we also make a LED where LED is hot at that particular point, and then we have a 4 piezo on the inside the fan, right? And then these are simulation. These are we need before that we need to make a grid dependency test, make sure that the result are not I mean consistent. I mean already acceptable. right? We see that the smallest mesh is the better one. Okay, and then this is the amplitude. This is synchronization. This one, if go like this, and then this one synchronization of the piezo, and then we can see that the piezo fan 1 and piezo fan 2 are frequency, right? This the vibration also increase with the voltage or amplitude, okay? And then these are synchronization take place. These are what we call the zero synchronization. This one 150 synchronization, right? Out of phase vibration. Sorry, this one out of phase, and this one is a phase synchronization, right? And then we study with the laser, and then we will see the flow behind and then forward of the piezo, and then we can see this vortex develop, because we try to avoid this vortex because we disturb the flow actually, right? That's why we need to study the vortex behavior, right? And compare this one PIV, and then this simulation, right? We can see that PIV and simulation give a comparable result, right? This is for single fan. We see that the flow with a different orientation, we can see different uh, apa? Flow, right? And then performance, different performance, right? If we see this flow type, okay? And then we see this distance from the tip to the surface is a 1 point something, and then 0.8, 0.1 there, right? This is how, okay? And then we make apa, dual piezo fan. This one we call it synchronization. This is out of synchronized that way, right? These are synchronized. That's how we will see the flow of the performance of the synchronization also, right? This is how the project is a mainly to do, right? And then we can see this the orientation A, B, and C, right? And then we can also check compression A give a higher amplitude, question B give a lower amplitude, and then the lowest one is apa on the orientation C. Sorry, my eyes not that good. Right, all right. This is how flipping, right, with the piezo. These are heat temperature on the surface, right? We can see that how here is less uh, better in terms of cooling, right? And we see that this one less better, and then we see, right? That's why A is a better in terms of heat transfer coefficient. We can see observe also on the surface, right? Okay, and then we use a double fin. This one, therefore 1 and 2. Say also we can see that synchronize one mean in phase synchronized give a better cooling compared to the apa out phase synchronized, right? And then compare a single fan is much higher in terms of temperature. Therefore, we can see that in phase give higher performance in terms of heat transfer, and then the worst one is a single fan, right? We can see that, right? Even heat transfer coefficient also show same thing, right? Also, we can see this one is a Nusselt number and enhancement ratio, right? We can see this the good in terms of heat transfer, and can also automatically better Nusselt number, right? And then we can see that effectiveness also become better there, right? For that particular position, right? And then we have a LED with a multi component PCB board, and then we can see in that LED there, and then we can see the temperature also give us a similar, right, in terms of performance. That mean this one is a temperature contour under force convection of T due 0.1, and then single vibration fan first row, and the second and last row of the configuration A and B of the dual apa vibrating fan, right? These are dual vibrating fan for both, right? At different orientation. Okay, these are all the result. We can say that heat transfer coefficient, and then also we have an average junction temperature. Also, we can predict at different amplitude, right? And then also we can see the heat transfer coefficient uh, with comparison with CFD and also experiment, right? Slightly, but it's still acceptable, right? In terms of variation, right? And then these are heat sink, LED, and piezo all together. We have a multi LED there, and then we have a fin without with fin and so on, right? Then we can see that this is the uh, delta, I mean the heat transfer resistance, resistance, the lowest one at that particular uh, position, and then we have these resistance for at different apa heat sink, dual fan, and then quad fan. I mean four piezo there. It give a lowest resistance there, right? Let's see, right? Then these are similar. This is the comparison of heat transfer coefficient between experiment and simulation, give a quite reasonable result, right? This is how we can get it. Similarly, these are uh, representation of the simulation, heat sink, where the temperature are vary along the surface, right? Okay, also we have many heat transfer coefficient. There's a junction temperature. We can see all are collected, and then we can observe that what we call it higher watt. We compare different watt, 16, 10, and 3.3 watt in term of power, right? Okay, by conclusion, we say that tip gap, minimum tip gap offering will provide best cooling performance. And then we see that in phase vibration, I mean synchronized one due to reduction of viscous drag and could further increase the vibration amplitude, whereby the smallest amplitude will detect at the out phase vibration at 130 degree. The fan enhanced the performance within approximately 2.3 times of the heated surface. By contrast, the dual fan enhanced heat transfer performance within approximately 2.9 and for the out phase vibration, and then 3.1 for in phase vibration, right? The characteristic of assembly heat sink cool by dual and quadruple vibration fan have been investigated. I mean, we already compare between 2 and 4, right? This how about this some of my publication, right? From the from the from the piezo fan, right? This all right. Now we are going to talk. Okay, some of my work are related to.
Excuse me, bro. Maybe we can stop here
Mm.
and we
Okay.
give some question
Okay.
and
Okay.
answer.
Right.
Yes,
At the last. Okay.
yes, please. All of you can ask anything before Prof Zulkifly continue the lesson. Ya, tadi beliau menerangkan tentang pemakaian piezoelektrik sebagai sistem pendingin yang efektif, bagaimana mengaturnya, memanagenya. Ya, tadi adalah hasil dari apa penelitian dari Dr. S3 Prof ya yang beliau bimbing. Seperti itu. Hasilnya cukup kompleks ya dengan grafik-grafiknya yang sangat banyak. I think it is very interesting. We can take it as a model. So please you can ask him any question.
Ideally, we want to replace the fan with a piezo fan. That is the idea. Normally, we have a fan, right? A rotary fan. Just tungkar kepada piezo fan.
Kipas
Kipas
dari
macam itu.
piezo
This the
material piezo.
the intention. Tujuannya macam itu.
Yeah.
That is why research is carried out.
Baik, kalau tidak ada, Prof, silakan
Okay,
dilanjut bila masih ada materi. Atau
Okay.
minum dulu mungkin, Prof. You can drink
Air
some.
saja, Mas. Air.
Sorry Pak, saya mau tanya ada di Zoom.
Ya, mana? Oh, saya tak boleh tengok ya. Orangnya ya. Ya, sila Pak. Ya.
Hello?
Ya, ya.
Yeah, so I just want to ask you if we look at normal cooling systems in PCs or like you say in laptops, from the device junction to the cooling unit, we usually connect them with some kind of media like a thermal paste, right?
Yes.
I want to ask, like in today's technology, is there any breakthrough or anything about thermal paste that is new since from what I read before when I was still interested in building PCs and things like that. I read that the what well, how do you say it? Not the success rate, but the how efficient the thermal paste is in being the media of conducting heat from the, let's say, the CPU to the cooling block is still kind of low if you compare it to things like liquid metals. Yeah. Like, but
Okay.
if you use liquid metals, it's gonna be so hard to remove, and sometimes it can even break the layer of the chips itself. So, is there anything in between the thermal paste and like liquid metals we can use actually?
Okay. All right. You are correct. We normally we use thermal phase, but thermal phase only for passive cooling because we need to have a heat. The thermal phase mainly to dissipate the heat. I mean, from the package to make it a spreader in terms of heat spread between the component from the hot surface to the other surface, right? Only that part we not consider here. We not study the thermal phase. We study basically cooling in terms of uh, the heat being transferred already from the chip to the fin, and then we want to remove that fin. We want to remove that heat. Of course, in between, you need to put it thermal phase there, but we don't study the type of thermal phase because thermal phase are vary. It is very difficult, and then normally industry don't disclose the type of thermal phase they use. Therefore, it is hard, difficult. We can also of course you can study that. It's no issue. But in this particular work, we not focus on the thermal phase, right? Is it I answer your question?
Oh, I
Of
see.
course,
So
thermal phase also very important. Yeah, I'm
just
no
out
doubt
of
of that.
curiosity, so in your experiments you use thermal paste there.
Yeah, I use thermal phase, but only regular thermal phase only. But we
Oh,
don't
I see.
study that thermal phase.
Okay,
We want
okay,
to study the
okay,
effect of the piezo fan rather than to focus on the piezo thermal phase.
okay.
But of course, thermal
Thank you,
phase
sir.
also important. Important. I'm not contest on that. It is true. It's important, right?
Okay, thank you, sir.
Okay, thank you.
Ya, silakan masih ada lagi yang ingin bertanya. Selamat datang, Prof. Di sini hadir bersama kita Ketua Departemen Pak Adi dan Pak Jati sebagai Ketua Departemen sebelumnya. Ya, terima kasih. Ya, baik, silakan dilanjut.
Boleh. Okay, masih Pak. Okay. Alright, basically, so actually, this one is about to study the heat pipe. Heat pipe, especially we focus on the PC cooling. I think everybody got a laptop, right? Inside the laptop, they have a PC cooling. They have a heat pipe. We're going to touch to see how much efficient of this heat pipe to cool the processor, right? Especially for the PC, right? Okay, we study both experimental and numerical study, right? Similarly, like I did, always my student must do simulation and experiment. This is my tool to study, right? Okay, this is a heat pipe. Normally, heat pipe have a elite type, elite, and then they have normally it's aluminium, right? Or copper, normally copper, sorry, copper, and inside they have the wick, wick, wick is a roughness of, bigger than how, right? The wick is to force the fluid through what we call the phase tension to bring a fluid to the condenser, right? And then, sorry, this is the liquid will be released there and then vaporized, and then it move to the condenser, from evaporator to the condenser. This is the size of the L-shaped flat heat pipe, right? Okay, this is the basically if you see your notebook, we have phase the heat pipe is like this. These are condenser side, the hot side. These are evaporators. Evaporator side, this hot side, and then these are condenser side. Right? They have a fan to blow, right, to cool the heat, to remove the heat. Right? And then inside they have a liquid. Right? Liquid normally below than the pressure is below the atmospheric pressure. Right? These are vacuum pressure then. Right? Therefore, when the steam or vapor comes here and then the heat will be dissipated from the condenser and then it become liquid. When it become liquid, the wick to carry them back to the evaporator, and then the process of cooling, heating, cooling, heating will be continue like that. Right? This is how. Alright, this is a characteristic of our L-shaped fin flat heat pipe. These are evaporator length. These are condenser length. The adiabatic length. Adiabatic length is the in between evaporator and condenser. Right. This is the width and thickness. Original diameter is this one. This the all characteristic of or dimension for the heat pipe. Right. This is how we do. We put it the heater at the bottom of evaporator because we want to control the power. Right? We can control the power and then we can control the heat. Right? The temperature. Oh, sorry. Right? Therefore, we monitor. I mean, we take the temperature of evaporator, temperature of condenser, right? By this computer and DAQ, and then we have a fan also, right? Full, and then we blow the fan. Fan also can we vary the speed, right? This is how the setup. Very simple setup, right? Very simple setup. We do it, and then we do some measurement on that, right? This is the parameter that we're going to calculate. Actually, we want to know what is a uh, base resistance, what is a between base to sorry, this evaporator pipe again, thermal resistance for heat pipe RH is a similar one, right? Okay. Okay, this is the in terms of total resistance. These are how we represent in terms of electrical resistance. And then we can also calculate. First, we calculate the K effectiveness, right? K effectiveness just to study the optimization, right? Optimization, how much we can optimize in terms of size of this size of heat pipe, right? That's why. All right, and then we use a DOE when you have experimental data, and then you can calculate the optimization using DOE by composite central composite design this one, and then we also do some simulation, right? We have a fin, we have evaporator there, these are condenser, and there's a equation. We assume that K effectiveness, we don't consider the liquid inside yet, but at the beginning, right? Just to make it a three-dimensional. If you consider three-dimensional with liquid evaporation, then it take a lot of computer time. It take huge and more difficult to simulate. Right? Okay, these are the equation we use. Right? We use the equation in terms of continuity, momentum, and energy. Right? Again, we also consider liquid width. Right? For the this one, when we consider 2D, when we consider 2D, we do it 3D for K effectiveness, and then we make it 2D for wafer. We make it a separate simulation, right? Because it's too complex, and therefore we do continuity, momentum, and energy, and then we calculate those equation, and then this is the model for 2D. 2D because we want to see only the behavior of the flow inside the heat pipe, right? These are uh, the surface of, I mean the thickness of the heat pipe. This one the width, and then this the outer internal diameter. Internal diameter, it go like this. This is the vapor. These are liquid. The blue one liquid. The red one is vapor. Right. There is the condenser. Condenser length. Then we study the flow, how the vaporization taking place inside the heat pipe. Right. Okay. This we do it 2D. Right. Okay, this is the equation we're going to consider during the simulation, right? These are boundary condition, right? We use and all those velocity and so on, right? For the simulation. This is the evaporator parts, right? And then we have a condenser part. These all those solid liquid interface, right? And then we study the different coolant flow rate. We have a Q certain lower, higher, and highest we use, and then we compare with natural convection, right? This flow rate mean is air flow rate lah. We blow at the condenser, right? We see that definitely we see that at lower will be higher in terms of thermal resistance. Sorry, thermal resistance, right? We have of course natural convection will be the highest one, and then the lowest one will be higher flow rate. We higher flow rate give a lowest in terms of heat transfer. I mean, in terms of thermal resistance, right? Okay, and then heat pipe resistance versus heat input for natural convection and at various coolant flow rate. This one we consider natural convection give higher, right? At different flow rate in terms of air flow rate. This is heat power, heat input, sorry. And then we will see that similar result lah. The highest flow rate give a lowest in terms of apa? In terms of uh, uh, ni RBP, RB, based to evaporator, right? This we use our DOE. We do some check in terms of optimization. We have a heat input as A, coolant flow rate as B, and we see how what is the optimum value, right? Right. This is the result optimization solution for heat input and coolant airflow rate. This give they mean this the highest one, K effectiveness. We see air coolant this one, and then heat input will be lowest at one, right? This simulation with a solid one, right? We see this evaporator, this a condenser. That means the heat will flow through from evaporator to condenser, and then we can see that how much temperature change, right? Along, and then this one at different conversion, at 820 watt. This one 35 watt is higher in terms of evaporator power. All right, this is how 2D. This is more on the what we call it heat flow inside the inside the heat pipe, right? We have a density of air, density of water and vapor, right? We plug into we put it in the what we call it fluent NCs, okay, and then we can see that this is the wall temperature of the heat pipe, only 2D, no? And then we compare with experiment is good enough, give a very comparable in terms of result, okay. And then again predicted temperature distribution along the heat pipe at 35 watt and coolant F flow rate higher one, and then comparison with the experimental result also give a very good also, right? That means the simulation are acceptable at that particular condition, right? Then we can study more detail what's happening inside. We can see that vapor, and then we have a liquid, blue one is a liquid one, and then the red one is a vapor one, right? We can see how the vapor moves and then go down, and then the liquid go down, right? At different at different power, 20 to 35 and so on, right? And then we see that at 20 also, we can see how the liquid and vapor interchange, the flow pass through up to, and we go down to the uh, evaporator, right? Maybe we can study more detail the condition inside the heat pipe, because we cannot see inside the heat pipe, right? Right. Right. I think we also can check the velocity also. What is the velocity between steam and also the water, right? Its flow. We can also measure, right, by the simulation. That's why simulation is very useful in order for us got more detail, more understanding on the physical behavior of the fluid inside, right? Right, we can also see vapor and liquid pressure also. If you want to know the pressure, you can see, right? Vary from evaporator to the condenser, right? Then we can see that liquid pressure below, and because we set zero at the condenser, of course, will be a zero there, right? I mean, we see a pressure drop there, right? Okay, inside the heat pipe, right? These are some reference we use, right? Based on the study, right? For the study. And then now I move any question we can have state, right? Or similarly, we use also heat pipe, but different heat pipe. This one just now is naturally induced the steam. This one we use a pump to pump it. And then we have a heater there, right? And there is flow. This flow, we can use a different fluid now. Now, whether we use what we call it water, or you can use a nano fluid, or you can use any fluid, right? But now we focus more on the nano fluid, Right? We want to put nanofluid inside this one. We want to see how effective of the nanofluid to cool this evaporator. Right? This is what the main task for this project. Right? Okay, this we use clear pipe glass, and then we can observe these are pure water, and then we can see that at this 20 watt, and then we see a bubbling in terms of water. But when come to nanofluid, we have the alumina. We cannot see that. But when come to diamond, also we cannot see. We put a diamond, artificial diamond. It's not real diamond, artificial diamond. Right? Okay. Okay, and then if we see 40, and then we see bubbling very big for the pure water, and then we have aluminum oxide, we have a small bubble, and diamond also very small bubble, right? We can compare how the nanoparticle that inside the nanofluid can absorb the heat, can absorb the heat compared to water. They don't have a particle there, right? That's how the system. This evaporator. This the heat pipe pass through like this, right? And then these are condenser, right? We have a fan to blow, and then we see based on simulation, and then we can see the evaporator go like this, and then it become cool, and then again fit to the and then we can see that the how effective the nanofluid compared to water, whether it is alumina or diamond, right? Okay, and then we can see also inside the how the nanofluid can distribute the heat, right? Compared to diamond, right? We can see also in term of heat dissipation inside the. Okay, and then we measure experiment and the simulation. We compare this the pure water. We see the temperature base one is higher, and then we have a diamond where is lower compared to them. That means diamond is very good to to be cooling for this particular setup, right? And then we check compare simulation also show a similar one. The diamond give a lower, right? Compared to water and also alumina, right? We can see that this is how comparison between experiment and also, and then we can see lah throughout where the location of condenser and so on, right? Evaporator temperature and blah blah, right? This is how we measured it, and then we compare with the simulation, right? And then we try to make it real life. We put in our computer, right? These are diamond because we found that diamond nanoparticle give a better, and then we plug in the diamond, and then we use for our computer. My student computer lah, not my computer. It's his student, my student, his computer actually, right? To use as a cooling medium for the processor, right? No need to use normal heat pipe, right? Okay, they put it. Okay. All right, we did some publication also with that. Fluid heat pipe, and then okay, I also any question that's finished for heat pipe before we go to solar cooling. We have another two, solar and battery cooling.
Ya, silakan teman-teman sekalian. Ya, yang online, monggo silakan teman-teman di Zoom yang ingin bertanya. Ya, baik Prof, silakan, tinggal sebentar lagi kan Prof ya?
Ya, sedikit
ya,
lagi.
Sedikit lagi insya Allah. Silakan.
20 menit lagi.
Tetap bersabar kita.
Yeah. Right, you must say. Okay, now it's an ongoing project. We are working on the PV solar power enhancement, and then we use at the moment, we have 3 PhD students are working on this. One of them are working on the fin, on the heat sink, some on the heat pipe, and then one of them is on the reflector, right? Reflector. They have okay. Now I combine together lah. If not very long to to go through one by one, right? Okay, this is the solar. Of course, solar nowadays are very important, right? These are over than 2,000 years now. We are living. We need to go to sustainable energy now, right? This is very, very important. And then the most promising one is solar, lah, right? Because we are in the equatorial, close to equatorial country, and then we must have we have a leverage of solar, right? Therefore, solar can be used is a clean and depletable electricity and heat generation application, inexpensive and realistic, right? Okay, because nowadays also petrol, gasoline are more expensive already. Therefore, it's good to have solar, right? Okay. Okay, solar cell, what we want to focus is efficiency, how efficiency behave. If we know that when efficiency have significantly improved over the years, is still facing challenges in reaching higher level. Improving the efficiency is crucial to make solar energy more competitive and with a form of energy generation. Current status of efficiency between these are efficiency of solar cost of solar panel have decreased. Nowadays it become cheaper and cheaper. The overall cost of the solar power system, including installation and maintenance, remains a concern for widespread adoption and innovation and economic of a scale are needed to further reduce the cost. Therefore, the cost, of course, will be still expensive, but slowly bring lower and lower, right? But it depends on the design, how you want to design your system, in terms of solar. Energy storage, this one also issue. Solar power generation intermittent due to variation of sunlight, and energy efficiency storage solutions are necessary for consistent power supply. Current energy storage technologies such as battery need improvement in terms of cost, efficiency, and environmental impact. Right? Storage also important because we don't know today is no sunshine, right? And then we don't have power. If we have storage, and then we can utilize that. Right? That's how. Okay, this is how we want to work. Try to take a benefit of this. First, we want to increase the PV by introduce the reflector. Reflector to bring more sunlight fall on the solar panel. If we more sun fall on the solar panel, we assume that we increase the power. Right? This is the reflector. Okay. Temperature increase, but again, when the temperature increase, the efficiency of solar will be reduced. With the hot, become hot, the solar panel will be reduced, decreasing the overall power output. The efficiency of solar module, PV module, increase as more solar radiation fall on the module, reducing of the PV module for same output power, reducing cost, reducing footprint carbon. Right? This is how if we put it reflector, right? Okay, this is the fin. If we put fin, we know that when these are solar cell become hot, if we can reduce the heat, and then we can improve the efficiency. Therefore, fin also, it is important if we want to study how to cool the to the solar panel, solar cell. All right. Okay, this is the sun. Maybe like this. This is the PV reflector. How much the angle, right? This is a reflector where. What is the best position of the reflector to put, and then how we can vary if the sun move from this go to different angle, right? So sun also very different because I don't know in Indonesia, but in Malaysia normally we have a good sun between 11 o'clock to 3 o'clock. This is the area we can get more solar, right? But maybe here also almost similar to that, right? Region, right? This is how, and then we try to put it the reflector better to make sure the sun fall on the solar panel, right? Okay, this is the study. Many people already study on the solar panel with a reflector also. Okay, they have declare many improvement, right? Already they have a 6.5, 12.2, even more than that, right? We have also 60%. The effect of reflector parameter output can go to up 60%, very high, right? 48%, they say, right? Use our V-through concentrator. And then these are how the the study have been carried out, been produced by the researcher. Now we want to again to again to study that to see how this one can give us reduction or improvement. Right? We use a solar light 782.5 watt per meter square. This we use a halogen ion halogen lamp, halogen halogen lamp, right? Halogen lamp just to mimic the sunlight because we cannot do outside, right? Because the student bit difficult. Sometimes they have there, sometimes they're not there. It's not regular there. It's quite tough. Then we do it halogen lah, and then this the apa fin, and this solar cell with the reflector. This halogen lamp then and then for into study, right? This and then this fin we study the beginning. This is not the final, and this early stage. This is a fin two fin. We have four fin and there are many fin type A, B, and C. These are solar cell very small. Study are very small, easy to handle, right? And then we put it like this. This is the halogen ion, halogen lamp, light bulb, and then the light will be fall onto that, and then this okay, something like that, right? And then they put thermocouple lah. These are thermocouple at the back, thermocouple at the top, and then also measure the power of the solar cell, right? And then this is the specification of the solar cell, polycrystalline solar cell. There's the size and power and so on, right? And then, okay. This is the condition what we want to measure. We do experiment. We run 18 times, 5 times 18, 5. This is the variable we control between solar cell angle, then also reflector angle, solar cell angle, and so on lah. And then this the parameter, the output, what we measure, the result, what we taking out from the solar cell, right? Okay. This is the without, this one without reflector first. We have the apa? Bare solar cell, right? This is the condition. If we use a angle from 0, roughly 0 to 100, this is the variation of temperature, right? Power, sorry, variation of power. Okay, almost even 100 or so, almost close to the 100. Also, the power almost consistent, right? This from solar cell. Then, okay, now when we put it solar cell versus angle, now we see that this is for fin type A, B, and C just now. 2, 4, 2, 4, and many. C is many. And then we see, of course, right? These are the surface temperature, right? Okay, we are no cooling one without fin is higher. We have many fin one is become lower, right? The result also show that if you put fin, it significantly reduce the temperature, right? If you put it fin, right? Okay, and then we see that power also. If you have you increase the power, see, significantly variation. You will slightly increase the power. These are very small. If big, it will be more power, right? Correct or not? This mean that type C is significantly increase the power compared to without the fin, right? The blue one, without the fin, without cooling, right? This only to put without the airflow, like without the blow the air and so on, right? Okay, and then we check these are temperature and maximum generated power from no cooling to type C, no cooling to type C. The maximum power just now, right? And in terms of surface temperature we see significantly drop, and the power significantly increase, right? This is the how when we put in reflector. Now, if we put reflector, and then we can see that the the angle of reflector play a very much is a very important role, right? Therefore, you need to find where is the best angle for the reflector, right? Because if you see this a power of solar cell. When this angle of reflector, we see there is a climbing, right? We see that looks like the blue one, this or green one, okay, suddenly increase, right? At 120, 100 to 120 lah, right? Something like that. 110 to 120 seems like the best condition of the angle, right? Okay, and then if you use a 4 reflector, this a 4, right? Just now is a 2, right? Only this side and that side, and then if you put it 4, and then also we see more distribution, more relaxed in terms of fluctuation. We see that again 120 to 110 and 120 give a better value of power, right? And then we see that these are 2 and there's 4. Of course, we see that power are better for the 4. And then as predicted, we use DOE to predict. Also, they predict 4 reflector is better, can increase slightly in terms of power. All right, that's how the results show. Okay, these are heat pipe. We apply that just now reflector with heat sink, and then now we put the heat pipe. All right, heat pipe on the solar cell, and then we put these are heat pipe. These are solar cell there, and then we have a halogen lamp from the bottom, and then to heat because heat pipe cannot stay the other way around, right? And then we take a temperature T1 to T8, and then we use a DAQ to measure those, and then we also control the fan speed of the heat pipe, fan speed blow. Okay, this how, and then this experimental setup we put it in the lab. Okay, we put it something like that. This is a temperature reader. These are to measure the sun, to measure the radiation, to measure the fan speed and so on, right? This is to control the fan speed and so on. These are heat pipe, right? Underneath is a solar cell. This is a halogen lamp, right? This is the setup we make in our lab, right? Very small setup only, right? And then we can see that from there we see, of course, has higher speed of fan will be a better result lah, in terms of power, and then of course in terms of power, right? In terms of power at different radiation different radiation is 2, 6 to 5, 7 to 5 give higher. The result is consistent. Say that the heat pipe with the higher fan speed give a better, right? Compared to the without, this one without heat pipe lah. The lowest one without heat pipe, all right? Also same thing, if measure T1, T2, also T1 give this one T1 and T2 the highest heat pipe with a fan give a lowest T1 and T2, and then when without itu give a highest. That is a consistent internal result, right? I think the final one. Okay, right? Can I continue? Quick one. This one is about also cooling. It's a battery cooling because this one we are want to study the effect of heat from the lithium ion battery. Okay, how we want to cool that. Right, this is a battery. We know that I think everyone know application can be anywhere. Right? The application is quite broad. Can use in the car, can use in the phone, can use also in the computer and so on. Right? Okay, but the danger is like this, right? Because it's be a flammable when become hot, and then it's a leak, and then it's flammable. Right? Therefore, it can cause a fire, right? Safety issue is a very crucial here, right? That's why if you want to go to take a flight, they ask you to remove the where is your power bank? It's your power bank like this, right? Because I worry about this, right? Okay, this is the electric car. I think everyone know. Normally they put under the right under the car, right? That's why everybody. If I buy the car, if suddenly flooding, how? I say, if normal car also flooding, you need to repair, right? It's not only electric car, normal car also if flooding already. Okay, right. This how density, lifelong, and then how to maintain those. That is the range of temperature that you need to make sure that when charging and no significant effect on the charging efficiency and life cycle. When you charging, you need to temperature at this range, right? This battery will be a degrade performance when the temperature are in this yellow board, right? When the higher temperature, then the battery will be poorer in the performance, right? That's why if for cooler will be better, right? Okay, this is the what we call the thermal management system, battery thermal management system, BTMS, right? We can use air cooling, liquid cooling, phase change cooling, or heat pipe, whatever you want to use it. This all right. Already many people are working on this, right? This is the battery. There's this one is a separator. This one is anode. This one is cathode. Then the ion interchange in between the separator there, right? Okay. This is the work of lithium battery. This is a cooling. This is a battery. Then this is a battery there. There is a cooling pad, right? There's a cooling channel, right? Liquid pass through the battery. All right, okay, right. And then we also have air cooling. We also have phase change cooling. We have a hybrid cooling, whatever you want to use, right? Okay, right. And then if we compare pro and cons, of course, they have various. Most are simple configuration for airflow. You can see phase change cooling will be more expensive sometimes. Okay, liquid application short range, low cost, simple structure, effective in controlling temperature, low operating cost and maintenance cost, moderate, higher installation cost, right? This is how pro and con in terms of different type of BTMS. All right, this is the experiment. I know there's in literature review. Literature review, we found that not many people, only a few people are working on the heat pipe with battery cooling. Right, it's good venture. It's good area to venture or to do a research. Okay, these are these are our battery pack. We pack it the battery. These are heat pipe together, and then we have a condenser there to cool. And then battery, when we start to use, right, when there is a charge or discharge, when it's discharged, more hot. When it's discharged, charging is not so hot, but stay hot, but not so hot. But it's discharged more hot. Therefore, cause the heat pipe to cool them, right? And then we use a system to control it. We use a thermocouple to measure the temperature and so on. This and then we do a nanofluid. We put it in the inside heat pipe. We use a few heat pipe, few nanofluid there, right? This is how we make a nanofluid, right? Nanofluid characterization with the stability. We use a measurement to make sure is that we calculate the stability also, and then we also check thermal property, physical property of the nanofluid, density, conductivity, CP value, and so on, right? And then, of course, we put it, the nanofluid inside the heat pipe, and then we test in the system, okay, our system, and then we also do some simulation like we did earlier. We do it a simulation. We see inside how the phase change and also evaporator and the condenser taking place. Right. This is the simulation of the heat pipe. Okay, and then we also do some calculation on the conductivity, density, viscosity, and so on. Right. And this one also the property of nanofluid, and then we do some result in terms of temperature, thermal resistance, and the heat transfer coefficient. All we can calculate it, and then we see that, of course, by using nanofluid with heat pipe with nanofluid is better, right, compared to the normal heat pipe, right? Okay. This also air, liquid cooling in terms of to cool the condenser, condenser length. Could also give a air cool, I mean, or liquid cool will be better, right? And then also this one, it is can you see, right? This the result what we have effect of the coolant velocity and flow rate between air and water, right? This the objective number 3, nanofluid versus water heat pipe. Experimentally, we can see that here the more average temperature, right? We have the deviation in terms of water, right? We will see that at this different uh, percentage concentration, right? We have 0.01, 0.05, 0.5, right? 0.5 give better in terms of heat transfer coefficient, right? Okay, compared to water. All right, these are also same. This compare between silica outside. These are alumina. Then we can see the how compared to the liquid water, right? This the, of course, inside the heat pipe, similar like last time. This phase change taking place between water, silicon oxide, and alumina. Okay. Similarly, I think this is what we found it. Water give a higher thermal resistance, and then silica oxide we give a less, and then these are also almost comparable to alumina, right? Then evaporator also give a heat transfer coefficient is better, right? For both nanofluid, right? Okay, with that, thank you very much. I hope. Oh, we just go, just knife.
Ya,
Time.
thank you very much, Profesor Zulkifly. Alhamdulillah, ya kita sudah selesaikan. Beliau, Prof, terima kasih banyak. Thank you very much for the lesson. Ya, Masih ada pertanyaan, mungkin kesempatan 1 saja, 2-3 menit. Kalau ada yang penasaran. Cukup ya. Ya baik. Ya, terima kasih sekali lagi. Sudah banyak kita berikan applause pada Prof. Zulkifly. Ya, terima kasih. Ya, sebagai penutup mungkin Prof. Zulkifly ini hari ini on time ya. Kita pesennya sejak beberapa bulan lalu minta 2 jam lesson, dan ini 2 jam betulan ya. 2 kali 60 menit ya. Tadi mulainya jam 1:05, ini sekarang lewat sedikit ya. Ya, dan juga kemarin itu saya jemput janji Prof, saya datang jam 9. Jam 9 saya datang kurang sedikit, beliau sudah nunggu di depan pintu hotel. Akhirnya tadi pagi saya datang, saya harus datang duluan. Jadi saya harus masuk hotel dulu baru beliau keluar. Gitu ya. Ya, terima kasih Prof. Jadi mungkin sedikit informasi kemarin, besok beliau akan membicarakan tentang publikasi Prof ya. Kemudian pagi harinya terkait dengan sistem instrumentasi, itu yang besok. Yang kemarin beliau sudah menyampaikan materi tentang artificial intelligence dan kesempatan studi di Malaysia ya. Barangkali kalau ada ingin tertarik tentang topik-topik itu nanti bisa didiskusikan lanjut ya. Terima kasih banyak. Baik, begitu mungkin saya kembalikan Mbak Fitri atau panitia, gimana agenda berikutnya. Pemberian Prof, mohon diterima ini sertifikat. Oh ya. Oh ya, baik, terima teman-teman sekalian yang ada di Zoom dan online lainnya. Terima kasih atas kehadirannya di siang hari ini, dan nanti seperti biasanya akan ada sertifikat yang diberikan dari panitia. Terima kasih ya.